In the last section, we were looking at how to approximate the area underneath a curve. Say the graph y equals f of x from x equals a to x equals b. And so what we saw was that if you wanted to just approximate it, well, what you could do is take that interval from a to b and split it up into a bunch of pieces. More pieces means more work, but also means a more accurate approximation. Then in each piece you'd pick some sample point, say maybe the midpoints. You'd see where those hit your graph. And then what you would do is build a kind of staircase function that serves as a good approximation to the function you have. So here we'd do something like this. Right, so here this function in blue, if I look at the area underneath that, that's going to be pretty close to the actual area that I want. And the actual kind of arithmetic that you did here was, we called these points, these sample points, this was like x1 star and so on, x2 star. So you're taking f of x1 star times delta x. Remember what delta x was when you have a and b and you have all these different x values. Delta x was just the width of one of these. Well, in fact, the width of all of these. Delta x was b minus a divided by the number of pieces n. So f of x1 star gives you a height, and multiplying by delta x, which is a width, gives you an area. And then you just add up a whole bunch of terms that look like this. So this is pretty close to what the actual area is under the red curve. Okay, and the basic, really important idea here is that as n increases, well, the approximation improves. All right, so you could sit down and do it with n equals 4 and then 40 and then, who knows, 40,000. And your approximations are going to get closer and closer to the actual area. Well, we've talked about things like this before where you have some quantity and you have a variable that you want to push to higher and higher values and kind of see what the trend is. That's the same sort of thing as a limit. So really what we want is to look at the limit as n goes to infinity of, well, of all of this stuff here. And so the idea is that the actual area, the real area, is equal to that. Or at least it usually is. So it is sort of for nice enough functions. Well, to make this a little bit easier to talk about, first let's introduce some briefer notation. So there's this idea of sigma notation. So first let me just introduce it in the abstract. So a typical piece of sigma notation looks something like this. Capital letter sigma from, say, I equals 3 to 7 of, let's say like I over I squared plus 1. What does this mean? Well, the idea behind sigma notation is that you're going to be adding up a bunch of terms that all kind of structurally look very similar. We use capital letter sigma because that sort of represents that I'm summing things. It's sort of like a big capital letter S. So the idea is that the bottom part tells you where to start. It's the first I value. So when I equals 3, you go and you plug that into the function that's sitting here on the inside. And so in this case, we get 3 over 10. Now I let I be 4, plug that in and see what I get. In this case, it's going to be 4 over 17. And I just keep doing that over and over again until I hit the top bound. So this top number is the last term. In other words, the last sort of I value. So in this case, we're going to have one for 5 and 6 and 7. And so that'll be 5 26ths and 6 37ths and 7 50ths. So you just treat the inside like a function that you are plugging the index variable I into. You write down all those separate terms, starting from 3 and ending at 7, and then string them along with plus signs. Okay, so it's just a convenient way of representing, adding up a lot of terms that are very similar. And so we had this expression just a little while ago that looked like f of x1 star times delta x plus f of x2 star times delta x all the way up to f of xn star delta x. And so we can write that very briefly as the sum from I equals 1 to n of f of xi star delta x. Right? And this particular sum of this form right here, you'll see referred to as a Riemann sum. So sometimes you'll see problems that will say to approximate an area, for example, using a Riemann sum. And they mean just do what we did in the last lecture, where we were approximating areas by picking sample points and so on. Okay, so the upshot then of all of this is that the area under f of x is equal to the limit as n goes to infinity of the sum from I equals 1 to n of f of xi star delta x. Now this is kind of a scary piece of notation here, but the idea is really simple. Remember that the idea here just says to add up these areas of a bunch of rectangles that we've sort of put together. These are rectangles under a kind of stair function that we built to approximate f. And then, well, this part here just says that the larger n gets, the better the approximation is. Well, it gets to be a little bit cumbersome to write down this whole expression all the time. And also it turns out that this expression, this appears in lots of places. So it's not just for finding areas. There are lots of physical and other geometric problems that end up looking something like this, something like taking the limit of a sum of f of something times delta x. So because of that, we make a new definition. It's just a new symbol. So we're going to call this the definite integral of the function f from x equals a to x equals b. So first what we have is just a new symbol, which looks like a kind of elongated S. We put the a down on the bottom and the b up top. Then we write the name of the function f of x, and then we write this extra little piece dx. For the moment, it's not maybe so clear what the dx means, but we're just going to include that. It sort of conveys that the x is the variable that we're talking about, and if you want to get into the habit of including that, because if nothing else, it will help your bookkeeping later with some of the later problems that we look at. So we have this, and what this symbol on the left means is it means exactly this big limit that we wrote up above, the limit of the sum of all this stuff. Okay, so this is just a new kind of thing. So now, of course, making a new piece of notation doesn't make anything easier to calculate. And for this lesson, we're still going to be a little bit stuck on this thing on the right-hand side. How do you actually find the limit of a sum like that? There are some functions where it's not so hard, but for most functions, even some relatively simple functions, it's really difficult to find a limit of this sort. And so we're going to have to try to find a way around it. But for now, let's just talk about how we can interpret a definite integral. So how do we interpret the integral from a to b of f of x? Well, one is that we've already seen. The whole point was that this thing on the right-hand side cropped up when we wanted to find the area underneath some function that was sitting above a to b. So if this is what the picture of your function looks like, well then in this case the integral of that function is equal to the area. Call this area A. However, we have to be a little bit careful, and this is something you should think about whenever you draw a picture for a math problem. I mean, despite what you might think, pictures are useful in math well beyond just geometry. But you have to be careful about whether your picture has some hidden assumptions in it. And in this case it does. I drew a picture of a function that was completely above the x-axis. So for example, what happens if I have a function where the opposite is true? I mean, it still makes sense to take f of these sample points times delta x and add them up and take the limit. The question is, what does that actually calculate? Well, now that the f values are all negative, I'm going to get a negative number out of all of this. So I'm not really finding an area anymore. But in this case, you're going to find sort of the next best thing. So if this is, again, a function now sort of below the interval from a to b, well, this region here has an area in it, some positive number that is the actual area of this, sort of forgetting about where the curve actually is, and the integral is going to give you the opposite of that area. Right, so to give just a really simple example, let's say that you have the function y equals -2, just a constant function from 1 to 5. Well, then this figure here is a rectangle, which has a height of 2 and a width of 4, and so the area is 8. But now the integral from 1 to 5 of this function, -2, is going to be -8. Okay, well, what happens then if you have a function that is sometimes positive and sometimes negative? Well, then we have some parts, say like this first part here and this third part here, that define regions that are above the x-axis and some that are below. And in this case, what the integral actually does is it adds up the areas that are above and subtracts off the areas that are below. So it sort of calculates what we call a signed area. Now remember, I'm not choosing anything at this point. We've defined the integral to be this limit of this Riemann sum up here. And so all I'm telling you right now is what happens if you actually take the limit of such a thing. So it just so happens that what that does is it calculates the signed area where it adds up the positive ones, the ones above the x-axis, and subtracts off the ones below. If you wanted the actual total area, if you wanted A1 plus A2 plus A3, well, what you would have to do is something like the integral of the absolute value of f of x. Because the absolute value of f of x would then take this red part down here and flip that part of the function to be up here, and so then you'd have this region up here instead. But it actually turns out that for a lot of purposes, you kind of want the integral to compute a signed area because of what the meanings of the areas are. And this is something we haven't gotten into just yet, But the same way that the slope of a graph can have some physical meaning to it, in fact, the area underneath a curve can have a physical meaning to it. And for most applications, it makes sense to have area underneath the curve kind of cancel out with some of the area above. Okay, well that's enough for now. We'll look at some examples next time.